Greetings, AP Statistics students. Mr. Eicher here. Sorry I couldn't be with you today, but I thought I'd walk through the notes that I was planning on doing. Happy Friday, September 18th. We'll talk about the empirical rule today. So I want you to know how to use the empirical rule, know what it is, and then secondly, calculate percentages with the normal distribution, which we'll be doing a lot in the future. In the previous class, I provided you this link on the empirical rule investigation. It's in the week 4 Schoology folder, so if you want to check that out, you can follow along in your notes. But I'm going to give you 3 approximately normal distributions, and for each of them, we're going to calculate the percentage of values within 1 standard deviation of the mean, within 2 standard deviations of the mean, and within 3 standard deviations of the mean. So for instance, here's a dot plot showing the weights in grams of 36 Oreo cookies. The mean of this distribution is 11.32392 grams, and the standard deviation is 0.081 grams. So if we take that mean and we add and subtract 1 standard deviation, subtracting 1 standard deviation would give us that value, and adding 1 standard deviation would give us that value. So what percent of observations are within 1 standard deviation? Well, I've kind of put a little box around everything from 11.311 to 11.473, at least as best as I could guess where those are. So I count 26 out of 36 of those dots are within 1 standard deviation. So we'd say 72% of the observations are within 1 standard deviation of the mean. We can do the same thing. Subtracting 2 standard deviations from the mean, we get 11.23, and adding 2, we get 11.554. That would be all of these are within 2 standard deviations of the mean. So we get about 34 out of 36, it looks like, 94%. And then lastly, 3 standard deviations of the mean, that would be 11.15 to 11.64. And then that would be pretty much all of them, it looks like. That would be 36 out of 36. 100% of the data is within 3 standard deviations of the mean for this roughly normal shaped dot plot. And then we could do the same thing on the next dot plot. Here's a dot plot showing the scores for 50 students on an algebra test. The mean of the distribution is 76.4, the standard deviation is 7.9. If you'd like to pause this video, see if you can calculate the mean plus or minus 1, 2, and 3 standard deviations from the mean. The value I got was 68.5 to 84.3. That would be everything within this little range there. And I counted 35 out of 50 dots, which is 70%, are within 1 standard deviation of the mean. And then minus 2 standard deviations is 60.6. Adding 2 standard deviation, I got 92.2. And that would be all in orange here. So counting those up, that's 48 out of 50, which is 96% of the test scores are within 2 standard deviations of the mean test score. And then lastly, 3 standard deviations away from the mean is this range. So we're counting all the test scores within 3 standard deviations of the mean, and that would be all of them. And then the last dot plot we have is about a baseball pitcher, total strikeouts for 32 games he pitched in 2009. So we could do the same process, calculate 1 standard deviation plus or minus. That would be all of those, which is 24 out of 32, 75%. 2 standard deviations would be between those values, everything in here, which is 94%. And then 3 standard deviations, we get those 2 values. And that looks like it's pretty much everything. That's an investigation that I was going to have you do, but I've given you all the answers, so we can jump right to this. Summary of the investigation, I'd like you to compare. Notice for these 3 very different variables, the weight of Oreos, scores on tests, and strikeouts, we get roughly the same value, but roughly the same value of what percent of observations are within 1, 2, or 3 standard deviations. So kind of the question is, if it were a true normal distribution, what percent of observations would be within 1, 2, and 3 standard deviations? So these numbers in blue I'm going to show you are the important part of the lesson today. It's actually 68%, which we were kind of close. We were down to 70. 75 is a little off, but 68% of observations would be within 1 standard deviation of the mean. And then 95 would be within 2. And then 99.7 would be within 3. To give you a picture, if you're a little more visual, 68% of data falls within 1 standard deviation of the mean. So you can see, and marked with blue arrows, I have -1 to 1, and then shaded in blue. That would be 68% of the area under this density curve. 68% of the data would be from 1 to -1. And then 2 standard deviations, 95% of the area under that density curve falls from -2 to +2 standard deviations from the mean. And then finally, 99.7% of the data falls within 3 standard deviations of the mean. Now the total area, I know it might be kind of hard to tell right here, but there is a little bit of leftover area in here. Anything greater than 3 or greater than or less than -3 standard deviations away. There's a little bit of area, but it's very uncommon. But the total area would add up to 100%. So that's the empirical rule. The empirical rule is also known as the 68, 95, 99.7 rule. It's called the empirical rule because a lot of data that we can observe, empiricism, right, is philosophy of observation. But the empirical rule tells us that we can observe a lot of real world data that actually follows this pattern that 68, 95, 99.7% of the data is within 1, 2, or 3 standard deviations. It's important to note, though, that this empirical rule only applies to normal distributions. If you're left skewed or right skewed or uniform, it doesn't apply to those. So let's do a couple practice problems. According to the CDC, the heights of 12-year-old males are approximately normally distributed with a mean of 149 and a standard deviation of 9. We'll answer 3 or 4 questions with this same context. Part A says about what percentage of 12-year-old boys will be less than 131 centimeters. So I've already given you a normal curve. You could always draw it if you don't have the notes. But 131 would be right here. The mean is right in the center. We use this Greek letter mu. It looks like a U, but it's actually kind of like a capital M for 149. And this would be 2 standard deviations, -2 standard deviations away from the mean. So there's a couple different ways that you could calculate this. But one approach you could use is what percent of observations are within 2 standard deviations of the mean. That would be 95% are within 2 standard deviations. And we want to know less than 131. So we want to know this area, less than 131. Well, if this middle part's 95%, then that leaves 5% in the 2 tails, since it's perfectly symmetric. So it looks like our answer would be 2.5%. Now that's not the area from 122 to 131. That's the total area. So you would do 100 minus 95 and then divide by 2 would be like the work that you would do there. So that's one example. Looking at example B, part B, about what percentage of 12-year-olds will be over 158 centimeters. 158 is right here. We want over that, so that's all of this area under the density curve. And the mean's right here at 149. So that would be 1 standard deviation above the mean, about 158. So we could say, we know that this inside area is 68%. So if we did 100 minus 68, that would give us both tails. That would give us this one over here too. So that's 32, but we only want 1 tail. So there would be 16% on the left and 16% on the right. So our answer would be 16%. Let's look at another example, part C, about what percentage of 12-year-old boys will be between 131 and 140. 131 is right here. 140 is right here. So again, there's a couple different ways that you can think of it. Students are always finding different ways that you could calculate this correctly. So I would recommend doing that shading so you can make sure your answer makes sense. If you got an answer of like 50%, that probably wouldn't make a lot of sense. If you got an answer of 90%, that's definitely not 90% of the area under that curve. So let's see, maybe we could start with this inside area is 68%. And then, so we know that it's gonna be less than, this one would be 16 and this whole thing would be 16. So we know the answer is going to be less than 16%. 16 plus 68 plus 16 is 100%. So we know it's going to be less than 16%. This area is, that area is 2 standard deviations. That would be 95%. So maybe if we subtract 95 minus 68, that would be 27%. 27% would be basically everything in both of those, this one on the right and the one we're looking for on the left. But they are symmetric, they're equal areas. So if we divide that by 2, we would get 13.5%. And again, there's other ways that you could approach that, but as long as you get 13.5%, you get the idea. And then question D, we have about what percentage of 12-year-old boys will be less than 155? Now this is a tricky one because where exactly is 155? Maybe like right there, and we want less than that. The problem that we experience is that it doesn't fall perfectly at 1, 2, or 3 standard deviations. So we can't use the empirical rule. We can't use the 68, 95, 99.7 because we don't know exactly where that 155 falls. So there has to be another approach, and that's the last part of the lesson that we'll transition to now. How do you find an area under a normal curve like this when you don't fall perfectly at 1, 2, or 3 standard deviations? So obviously the means here, 1 standard deviations there, this is somewhere in between those. So the approach that we use is this. We draw a curve and shade the area that we're looking for. We convert the boundary to a z-score. This is one of the reasons z-scores are so important. And then we'll use table A to find the percentage. Table A is in the back of the textbook. It's posted on Schoology. It was also in these notes if you're able to print these notes. Table A looks like this. You do not have to memorize table A. It's provided on the AP exam. But table A basically is giving us areas under a curve. It's using calculus to calculate an area under a curve. And since we don't have calculus knowledge in this class, not all of us, we use this table instead. Also in a future lesson, I'll show you how to use technology to calculate these numbers. But at this point, we're just going to use the table. So looking at this question that we just had, less than 155, right? That was 155 is right here. And less than that's over here. So that's our first step to do the shading. We convert that to a z-score. So the z-score would be 155, right? Our formula for z-scores is x minus mu over sigma. X is the observation, also known as the boundary. And we subtract the mean, which was 149, and we divide by the standard deviation, which is 9. So it looks like we get 6 over 9, which is 0.67, we'll call it. So our z-score is 0.67. So once you have that z-score, you go over to the table right here. That's our z-score at the top, 0.67 in red. And on the right side of the table, you're going to find the positive, kind of erased it there. You're going to find the first decimal, so 0.6. So you're going to look for 0.6 where it says Z in that column, 0.6. If you're on negative 0.6, you want to be on the positive side. Table A has 2 sides. So we're looking for that. So looking across that row, it's one of these numbers is what we're looking for. And then we look for this digit, the hundredths place, which is right here, 0.07 is 7 hundredths. So then we go down the column like that, and lo and behold, where they intersect, the column and the row, that would be our answer. That would be our area, that number right in there, 0.7486. So we would say, to answer this question, we're looking for the probability or the percentage of heights that are less than 155 centimeters. We convert the height to a z-score. So notice I've changed the notation. The height has now been standardized to a z-score, and 155 was standardized to 0.67. And from our table on the previous slide, we got that answer of 0.7486. So we'd say 74.86% of 12-year-old boys are less than 155 centimeters tall. Let's look at another example using the table. Notice our last example, we had area below a point. On this next example, we have area above a point. There's going to be one extra step that we have to do. So it says about what percentage of 12-year-old boys will be more than 133. 133 is maybe right here. And you want more than that. So that would be the area under the curve over here. So it looks like a pretty big area, pretty big percentage of 12-year-old boys that are more than 133 centimeters tall. So the first step is we find a z-score. Uh-oh, gave away the answer. We find a z-score with this formula. So we would have the z-score, we have to convert that 133 into a z-score. So we'd have 133 minus 149 over 9. And calculating that, we get a negative z-score. It's negative because the height is below average. We get negative 1.78. So we go to our table. Our z-score is negative 1.78. We're going to first be looking in this first column for negative 1.78. And negative, these are positive. Oh, the other side, the table A has two sides. It has negative z-scores on one side. So see all these negatives here, all these negatives. And it has positives on the other side. So look for negative 1.7, which is down here, negative 1.7 for the first, the 10th place of the z-score. So that's that one. And then you're going to look for the second decimal place, the hundredths place, under the 0.08. So that's that one. And then lo and behold, we get this answer. The area is 0.0375. So if we go back, and we would say this blue shaded area, we want the probability the height is greater than 133. We standardize the height to be a z-score, which is the z-score of negative 1.78. And we get an answer of 0.0375. There's a problem here though, right? This is a huge, huge, huge blue area. It looks like it would be bigger than 0.375. The issue is the table A always gives you a percentile. It always is that boundary or less. So really this side is 0.375. So you got to do a little bit of math to calculate the answer here. You would actually do 1 minus 0.0375, and you would get a much more reasonable answer, 0.9625. So we'd say 96.25% of 12-year-old boys are more than 133 centimeters tall. That was it for the lesson. You have an empirical rule exercise and a normal distribution above or below exercise on Khan Academy. Be careful if the question's asking you above or below. There's also an article that I'd like you to do. There's a Unit 1 to 3 FRQs assignment on Schoology. And today or tomorrow, I will be grading the Unit 3 FRQs. So make sure they're done by Friday, September 18th. And then your Monday assignment, you have a video to watch. That's the area between two values. So make sure you watch the video and then do the exercise to make sure you understand that. Also on Monday, September 21st, I think it would be, I will be inputting your Unit 3 unit test and mastery. So make sure if you don't have a high score on the unit test or mastery that you complete that before Monday morning. Thanks for watching this video. Sorry I couldn't be with you, and I look forward to seeing you next week. Bye.